Welcome back, everybody. Please take your seats. It is my great pleasure to introduce the first speaker this afternoon. Hubert Lacoin is my colleague here at IMPA. He got his PhD from Paris in 2010 and became a professor at IMPA in 2014. He works in probability theory, especially in problems inspired by physics. He has received several awards. In particular, he was an invited speaker at the virtual ICM this year. Today, he's going to tell us about mixing time and cutoff for one-dimensional system. Please, Hubert.
So, thank you very much, Carolina. It's a great pleasure to give a talk. Can you hear me? Okay, so it's a great pleasure to give a talk in this nice institute where I've spent most of the last 10 years. What I'm going to talk about is partly joint work with Pietro Caputo from Rome and Cyril Labbé from Paris. And the object of the talk is to try to have a look at relaxation to equilibrium of particle system. So as an introduction, I will want you to consider the following physical situation. So let's imagine that you have a two-compartment box. One compartment is initially filled with a gas of particle, and the other is empty. What is a gas of particle? Well, it's just a very large number of small spheres. Okay, each of them can be described by the position of its center and its velocity. And the rule of evolution of your gas is simply the following. I mean, your sphere, when they have no obstacle, they just move ballistically. Okay, they don't feel any acceleration from anywhere. When they meet the boundary of the box, they will just bounce, conserving their velocity and return with the same angle. And when two particles collide, well, they will just bounce on each other in a way that preserves kinetic energy and total momentum. Okay, so now let's assume that initially your system is at equilibrium, and I will not dwell too much on what that means, but okay, just keeps the idea of physical equilibrium. And what we do is we open the membrane that separates the two compartments, and what you will see is that the gas will start to invade the other part of the box, after some period of time, the system will thermalize, it will come to equilibrium in the sense that what you will see will be an homogeneous density of particle, but now on the full box instead of just one compartment. What I've just described to you is a dynamical system, and I'm a probabilist, so maybe I should not talk about that. This is something you can prove rigorously. I mean, you can make sense of the statement. You can give a mathematical sense to the statement I just gave you, and you can prove that this holds. But it's very difficult then to say anything more, to say at which speed this thing occurs, how much time you need to wait. For this reason, in order to be able to give a more accurate, a more quantitative description of this relaxation, I'm going to take huge simplification to this picture. So the simplification I'm going to consider are, first, I will make the system random. So, this is actually the most reasonable simplification of the three I'm presenting here. The system I presented you, it's completely deterministic, but it's very chaotic. So if you change just a little bit the initial condition, basically, the first collision of particle will be very different. And therefore, I mean, a very small change in the initial condition will change a lot your system after a short amount of time, actually, so that even if your system is deterministic, it kind of looks random. So making it random is not so much of a drastic change, and it helps a lot the analysis. The two other changes are really, well, to make our life as easy as can be so that we can prove things, okay? So what we are going to do is to consider a lattice model. So a particle will now live on a discrete space instead of in a continuum, and we will make it one-dimensional. Okay, so I think with this, now I can introduce you, well, the system will be the main object of the talk, which is the symmetric simple exclusion process on the segment. So I'm considering a segment which is made of n slots, and I'm considering a number k, which is somewhere between 1 and n minus 1. And k will be the number of particles, and well, a configuration of the system will just be well, a way to arrange these particles on the slots. Each particle should go into a slot, but one slot can host at most one particle. Okay, and then we want to look at a dynamical evolution of the system. Well, it evolved by discrete steps. So let me describe you what a step looks like. So the first thing you do is you select a particle uniformly at random amongst the k particles you have. Then you choose a direction in which the particle will want to jump. So well, to do that, you just toss a fair coin. And then if the jump is possible, you make the particle jump in the direction that you've selected. So here, let's say that I've selected right, and the jump is possible, and I will tell you a bit more about what this means. So the particle jumps to the right. So now let's look at the second step of the system. Okay, we're just repeating this all over again. So select one particle. Let's say that this time it tries to jump right. Now you see that the site on the right of the particle, it's already occupied, so the particle cannot jump. Okay, so the jumps, they will be validated only if the site on which the particles try to jump is unoccupied, and the site has to belong to the segment. So if you select a particle at the extremity of the segment, if it tries to go right, well, the jump will be cancelled as well. Okay, so now I have to tell you when the steps are performed. We are considering, I mean, this is just for convenience, we are considering a system in continuous time. So the steps, they are occurring at random time, and the time between two steps, they are exponential variable at mean 1 over k. So what this means is that basically each particle will try to jump with rate 1. Okay, so I mean, basically each particle will have its own clock, okay, that jump with rate 1, and when it's the particle of one, the clock of one particle is independent of the clock of the others, and when this clock rings, particle try to jump. Okay, so this is the process in the symmetric version. You can also consider an asymmetric version of the process where it's exactly the same thing, except the step where you choose the direction, you make your choice asymmetric. So you have a parameter p, and you will just choose to go right with probability p and left with probability 1 minus p. And let's say that, well, our system is biased to the right, so p is something between 1/2 and 1. And well, this can model, for instance, a case where you have your gas of particle is submitted to an external force, or for instance, in another domain, it can also model car traffic, okay? Well, just any system in which you would like to have a bias. Okay, so now let me just be a tiny bit formal for a moment. So our process, the exclusion process on the segment, it's a random process, and we have to describe its state space. So the state of configuration in which it's taking values. So for this, I just encode particles by 1 and empty sites by 0. So a particle configuration will just be a 0, 1 valued function. And our state space will be the set of those 0, 1 valued function for which the sum of the psi x is equal to k, okay, because your number of particles is fixed. And this random process I just described you, it has two properties that will be interesting to us. So first, it's a Markov chain. So what this means is that basically, in order to know about the future of your system, you only need to know about its present state. So, of course, what I just said is wrong. You need to know about the present state and extra randomness, okay, which depends on, which comes in at each step. But what this means is that really, if you know about the present state of your system, knowing about the past won't help you to predict the future. Okay, this is what is called the Markov property. And another property it has is that it's irreducible. And this simply means that if you take two pairs of configuration, you can always go from one to the other infinitely many steps. Okay, so this is, okay, these two things, they kind of come almost directly from the construction. Well, maybe for irreducibility, you have to work a little bit, but this is not much, okay? And if you take this property and a probability textbook, what you can get is, the following interesting result is that, okay, if you let eta t psi to be our random process starting from initial condition psi, what you have is that when time goes to infinity, the distribution of your process tends to a limit, which I will call pi, and this limit does not depend on the initial condition. Okay, so this measure pi is called stationary or equilibrium measure. The name is justified by the fact that if you start with an initial distribution which is distributed according to the stationary measure, then at any given time in the future, the distribution will remain the same. And what I want to talk about in this talk is really quantitative aspects of this convergence when the size of the system and the number of particles go to infinity. So, here I will just consider that k goes to infinity. K will be just alpha times n, where alpha belongs to 0, 1. Okay, and you round it to the next, to the nearest integer if you want. So the number of particles will go to infinity proportionally to the size of the segment. Okay, so before starting this, maybe, okay, what I just told you did not tell you anything about pi, and it turned out that this equilibrium measure is not difficult to compute in this specific case. So I will not do the computation, but I will tell you what it is. So it depends on whether your P, or whether the system is symmetric or not. So if the particles jump symmetrically, pi is simply the uniform measure on your state space. So that meaning that at equilibrium, typically particles are spread out, and actually if you look at a fixed region of the system, what the system looks like is really IID Bernoulli variables with parameter alpha. Okay, they are not fully independent if you look at the whole segment because you have a constraint on the sum, but this is not something you see locally. On the contrary, when P is not equal to 1/2, okay, well, if P is larger than 1/2, then at equilibrium, what you see is that essentially all particles are packed to the right, and if you want, all empty sites are packed to the left. So it's not exactly this, but it's a very small perturbation of this, in the sense that, well, you have a region in the middle where particles may alternate with empty sites, but, well, okay, the size of this region is something random, but it's something of order 1, okay, in the sense that the size of this region remains tight, okay, when you send n to infinity in probabilistic terms. Okay, so two very different equilibrium measures. Okay, so now, okay, let me announce what I will do next. So first thing we will look at is a macroscopic aspect of convergence to equilibrium. This is called hydrodynamic limit, and this is basically looking at the evolution of the density of particles. So what happens if you look at your system from far away? Well, this is not something I've been working out, but this is really related to the second part, and this is also something other people at IMPA, like Claudio and Milton, are specialists, so they will correct me if I say the wrong things here. Then I will come back to what we want to, which is a microscopic approach of relaxation to equilibrium. Well, in technical terms, this is what is called mixing time for Markov chains. And once I've introduced you to the subject, I will tell you about our contribution to the field, which is mixing time results for exclusion processes. Okay, so what are hydrodynamic limits? So as I told you, it's just looking at the evolution of the particle density. So what do I mean by this? Well, I'm going to assume that I start from an initial condition which approximate well a density profile. So I'm saying an initial condition. What I should say really is a sequence of initial conditions, because the size of the system is going to infinity. So I'm really considering one initial condition with for each n. And what I'm assuming is that I have a function rho 0 such that for every a and b, the number of particles between an and bn is very well approximated by n times the integral of rho 0 between a and b. Okay? Well approximated in the sense that the correction term is little o of n. So for instance, if I'm considering that initially I have alpha n particles and they are all packed to the left, then initially I have a density profile which is given by the function indicator of 0 alpha. Okay, I have density 1 on 0 alpha and density 0 on the rest of the interval. And finding the hydrodynamic limit of the system, it's well, first finding the time scale on which this density of particle will move, and then finding a density profile, so a density that changes with time that will just approximate, will give you the density profile of your particle system at all times. So what I mean is that you should try to find rho tx, which is such that for all t, at time theta nt, the number of particles between an and bn is given by n times the integral between a and b of rho tx times n plus a smaller order correction. Okay, so just the same thing as before, but now you want things to be satisfied for all n. So why should such a thing be true? Well, the idea is that, well, you have lots of randomness of your system, but they come from lots of independent sources, so it's not unreasonable to kind of look for a law of large number for your system, okay? And this thing is really the, okay, it's a law of large number for a system with a high degree of freedom, okay? So, okay, so now let me tell you what hydrodynamic results have been obtained for the exclusion process, and starting with the symmetric case. So here there is a typo, so I should rewrite the equation. So okay. So, okay, in general, these hydrodynamic limits, they are given by solution of a partial differential equation with initial condition rho 0. Okay, the symmetric simple exclusion is somehow one of the simplest systems for which you can derive hydrodynamic limits. It was proved that in that case the time scale is n squared, and the equation is simply, well, the heat equation on the segment. Okay, I forgot about the 1/2 here. With a Neumann boundary condition. So the derivative of the density at all times should be 0 at the boundary of the segment. The first paper in which I've seen it appear is this one by Kipnis, Ola, and Varadan. But actually, in this paper, they prove much, much more than this. Okay, they prove a result which is valid in any dimension and large deviations. So I would suspect that this was probably known before as a folklore result. Okay, but maybe Claudio can correct me on this. Okay, now let me describe to you what the profile looks like in a specific case. So let's say that we start with an initial density which is the indicator of 0 alpha. So initially, all the mass of my solution, all the mass of my density is packed on the left. What will happen is that, this equation will immediately smooth the solution, and it will become flatter and flatter. And in the large time limit, rho tx will tend to alpha, which is simply, well, the constant which is equal to the total mass of the solution. Well, the flat profile is approached when t goes to infinity, but it's never attained at any finite time. Okay, so it's not a very deep consideration, but I wanted to tell you this because this will contrast with what we are going to see on the next slide. So in the asymmetric case, the picture is very different. So in that case, the time scale is not n squared anymore, it's n. So here I'm writing n over 2p minus 1 so that I have no dependence in p in the equation, but this is a personal choice, okay? You could. The hydrodynamic equation you obtain is this one. So dt of rho is equal to rho 1 minus rho. So it does not look too nasty, but actually it's not a nice equation. You have to carefully look at what the notion of solution you want to consider here if you want to have uniqueness of solution. On the segment, you also have to be quite careful about the boundary condition. So this result on the line was shown by Reza Hanlu, and there were particular cases of this result that had been known before, starting with Rost in 81. The case on the segment, how to well define the equation on the segment was done by Labbe in 17, and the hydrodynamic limit was proved in our joint paper in 19. Sorry?
On the right-hand side is dx.
No, there is no dx. There is no dx. There is dx? Okay.
It's the first one.
On the right, there is no dependence on x.
No, there is, okay, rho is rho xt, so there would be a dependence on x, okay.
For x fixed, it would be just a function of t.
Okay. Well, okay. Maybe okay. I would have to check. But what I'm going to say next is true. So, okay. So let's look now at the evolution of this density profile in a specific case where rho 0 is the indicator of 0 alpha. And what happens is that, immediately the density becomes continuous. Actually, the shock you have in the middle becomes a linear part. So, okay, so the density, there is a segment that is created in the middle of your big segment on which the density evolves linearly from 1 to 0. And then when the region where the density is positive reaches the boundary, or here I've taken alpha is equal to 1/2, so this, by symmetry, this happens at the same time as the region of density smaller than 1 reaches the left boundary. What will happen is that the mass will accumulate on the right on the segment, and the absence of mass will accumulate to the left of on the segment. So your solution will start to look like this, okay? And the zone of density 1 and the zone of density 0, they will progress until you reach the fixed point. So now this is the fixed point of your equation, and it's reached in finite time. So it's really different than in the symmetric case, okay? And this is true from this particular initial configuration, but this is actually true for any initial configuration with total mass alpha. Okay, so this is what I wanted to say about hydrodynamic limits, and now I'm going to focus on more microscopic aspects of convergence to equilibrium, for which I'm more competent, maybe. So let me tell you about mixing time for Markov chains. So if you remember what we saw on an earlier slide is that when t goes to infinity, the distribution of eta t psi converges to pi, which is the equilibrium measure when t goes to infinity. And we want to quantify this convergence. So if you want to have a quantitative version of this convergence, you need to consider a distance on probability measures. So the distance we are going to be considering is total variation distance. And if you consider two probability measures on the same state space omega, the total variation distance between them is just the maximum over all events A of the absolute value of the difference of alpha and A and beta of A. And this actually measures how well you can couple a random variable with distribution alpha and a random variable with distribution beta. So for instance, if alpha is equal to beta, this total variation distance is equal to 0. Okay, what we have is really a distance. And this total variation distance is equal to 1, which is the maximal value, if and only if alpha and beta are mutually singular. Okay, if and only if they have disjoint supports. And for a Markov chain with a stationary measure pi, we define the distance to equilibrium as the total variation distance between the distribution at time t and equilibrium. And what we are going to take is with the worst possible initial condition. So we maximize over all possible initial conditions. And now if we fixed a threshold epsilon between 0 and 1, we will define the epsilon mixing time of our system as the first time for which the distance to equilibrium drops below epsilon. And maybe this is not completely obvious from the definition, but this dt is monotonous in t. So if you drop below epsilon, you remain below epsilon at further time. Okay. So yes, so now that I've introduced this, okay, let's try to familiarize with this notion by considering okay, a relatively easy example, and it's actually a particular case of our particle system. So let's consider well, the exclusion process, but now with only one particle. So it's just a simple random walk on the segment. So in that case, your equilibrium measure is just a uniform measure on the segment. And if you want to look at the distribution at time t of the random walk, what will happen is that, well, from the central limit theorem, okay, if you're on the full line and not on the segment, you know that typically the particle will be at the distance square root of t from its initial condition. And that, well, actually, you will have the distance with, from the initial condition will be given by a Gaussian random variable. So therefore, if you take a time t which is much smaller than n squared, okay, well, the particle will have not seen the boundary of the segment, and its distribution will be concentrated on a small region of radius square root of t. So that this means that the distribution will be in total variation distance very far from equilibrium. So here the total variation, in that case, the total variation is very close to 1. Now, if t is of order n square, basically square root of t is of the same order of n. So the distribution of the particle, it will be, well, it will be a Gaussian which is kind of reflected on the boundary of the segment. Okay, reflected actually several times. So our distribution is now spread out on the segment, but it's not homogeneous. So now in that case, the distance to equilibrium, it's nor close to 1, it's not close to 1 nor close to 0, it's somewhere in between. And if t is much larger than n square, then, well, because of you have lots of reflection, then this profile will flatten out, and now you have a distance to equilibrium which is very close to 0. So if you fix epsilon and you want to know what's the epsilon mixing time for this simple random walk, what you will find is that, well, the mixing time is of order n square when n goes to infinity. And with a bit of work, you can actually identify the constant that should go in front, and this constant should depend on epsilon, okay, because of the analysis I've just shown to you. Okay, so this is what happens in the symmetric case. So now what is happening in the asymmetric case? So if you consider an asymmetric simple random walk, well, the equilibrium measure is very different. Now at equilibrium, basically, the particle is on the right on the segment. I mean, it's on the distance between the particle at equilibrium and the right of the segment. It's a geometric variable of parameter rho, which is just 1 minus p over p. Okay, so now the worst initial condition to reach equilibrium is intuitively starting from the leftmost side on the segment. And the mixing time should be given by the time you need to travel through the segment to reach the right. Okay, so now you're jumping left with rate p, jumping right with rate 1 minus p. So overall, the particle has a speed which is 2p minus 1. So because of law of large number, the time you need to reach to travel through the segment is n over 2p minus 1. And this gives you the mixing time at first order, and you see that this time it does not depend on epsilon. In order to get a dependence on epsilon, you actually have to look at the second order term in the mixing time. And the second order is basically looking at the second order, well, the second order term in the time you need to travel the segment. And this second order term, it depends on, it's random, and it's given by the central limit theorem. Okay, so you're traveling ballistically with square root of n fluctuation, and therefore this second order term will be of order square root of n, and this is where you will see the dependence in epsilon, because this is where you see the randomness of the system. Okay, so, well, what can we say of the comparison between the two things? So there is a difference between the symmetric case and the asymmetric case. That, well, the first difference is that the time scales are different, but this is not essential. The biggest difference is that in one case, once you have rescaled time, the distance to equilibrium drops smoothly from 1 to 0, whether in the other case, it drops abruptly from 1 to 0 at a specific time. Here, when n goes to infinity, this profile converges to a step function. And, well, you might tell me, well, this is because there is a drift in the system, and this kind of triggers this kind of behavior. And this is actually not true, in the sense that in the realm of Markov chain, this might actually be the most common behavior, and this also occurs for very symmetric systems. So people who first found out about this were Aldous, Diaconis, and Shashani in the 80s, and Percy is here in the audience. And they prove that this occurs for actually random walk on groups. So random walk on the permutation groups, random walk on the discrete hypercube. So for Markov chains that have a high, that are in a sense high dimensional, that have a high degree of liberty. And they gave a name to this phenomenon, which is cutoff. Okay, well, this is what I want to talk about today. Our results are cutoff results for the exclusion process on the segment. Okay, so let's start with first with the symmetric case. And in the symmetric case, if well, you consider the symmetric simple exclusion on the segment with a density of particle, the mixing time at first order is given by 1 over pi square n square log n, and the next order term is of order n square. So here, okay, because you have no dependence in epsilon in the first term, this means that cutoff holds in the sense that I've given in the previous slide. And well, the lower bound for this, the mixing time was proved by Wilson in 2004. He had an upper bound that was off by a factor 2, and well, the upper bound of this result is due to myself in 2016. Okay, and now let me come to the asymmetric case. So when you have a bias in the system, then the mixing time depends on this bias, but also on the density of particle. And at first order, it's given by this. So alpha plus square root of 1 minus alpha square divided by 2p minus 1 times n plus a smaller order correction. And our result is actually sandwiched between an earlier result and a later result. So Benjamini, Berger, Hoffman, and Mossel had proved earlier that the mixing time was of order n, but without identifying the constant. Okay, there are two different constants for upper and lower bounds. And after we proved this, Buffetov and Neja, they identified what is the second order term here in a sharp manner. So they proved that the second order is n to the 1/3 with a specific prefactor that depends on epsilon. And well, this n to the 1/3 is, okay, I won't be able to explain you why it comes into the game, but it's quite interesting because if you remember well, when you have only one particle, the second order term was n to the 1/2. So there is really something special happening here. Okay, so maybe to conclude, I will try to give you not a proof ID, but some kind of heuristic of why these things come, why this quantity comes in the mixing time, because, I don't know, this 1 over pi square n square log n and this expression here, they might look a bit mysterious, so I will try to provide some explanation for this. So let's start with the asymmetric case. And this expression you have for the mixing time, you can interpret it as a product of two things. So the first thing is n over 2p minus 1, which is the hydrodynamic time scale. And well, the second term is this thing which has yet to be interpreted. But what happens is that, okay, it's probably the wrong equation, but this quantity is square root of alpha plus square root of 1 minus alpha to the square. It's the time that your equation needs to transport the step function where all the mass is on the left to the step function where all the mass is on the right. So this kind of matches what you think of what the process should do. You know that at equilibrium, all the particles are on the left. Okay, this is what I told you some 20 slides ago. But and so the worst initial condition is probably when you have packed everything on the left. So, okay, maybe the mixing time is when at least seen from far away, okay, for the microscopic limit, the mass has been transported from left to right. So actually, this is in a sense a rigorous proof of the lower bound, okay? as soon as you've already proved the hydrodynamic limit. But you need more work for the upper bound because you need to check that things are not messed up at the microscopic level. Okay, so now let me tell you a bit about the symmetric case. So in the symmetric case, the expression for the mixing time is, again, the hydrodynamic scale times log n over pi square, which we have to interpret. So what I told you is that at equilibrium, your measure looks like a product measure. Okay, so like a Bernoulli measure with independent Bernoulli with parameter alpha. So if you look at the number of particles in a segment, well, you know that at equilibrium, in first order, it will be just alpha n times the length of the segment. But at second order, you will have fluctuation of order square root of n given by the central limit theorem. So if you think of this fluctuation in terms of density, after you have rescaled, there are fluctuations of order n to the minus 1/2. And then you might think, okay, my hydrodynamic profile, it never gets fully flat. But maybe if I can get it flat with an error of n to the minus 1/2, I mean, basically, well, the defect of flatness is comparable to the fluctuation I observe at equilibrium, so this should not be so bad. So what I should look at is n squared times tau n with tau Tn, where Tn is such that, well, fluctuations are of order n to the minus 1/2. And now we are actually with a simple problem of functional analysis, okay? So we want to contract, okay, we have initially fluctuations of order 1. We want to contract them into order n to the minus 1/2. So we want to contract them by a factor square root of n. And in order to find the rate at which these things are contracted, you just have to look at the first eigenvalue of this operator on the segment with Neumann boundary condition. It's not 2 over pi square, it's pi square over 2. But this tells you how much time you should wait in order to contract by a factor square root of n, and this is exactly log n over pi square. Okay, so I will try to browse very quickly about other contributions that have been made in the domain, sometimes in other directions. So I focused in one dimension, but actually there are things you can say in a higher dimension on the grid. So the cutoff question is open, but Yao and Yao and later Ben Morris, they have proved. Well, they found the right order of magnitude for the mixing time on a square grid or on a cube grid without identifying the right constant. And my colleague Roberto Oliveira obtained a result in the same flavor for completely general graphs. People have also looked at particle systems with a reservoir where you're allowed to add and subtract particles from the boundary, so including Milton and Patricia in the audience. Well, what has been proved recently by Justin Salez is that actually for systems with reservoir, you can prove cutoff for a very large class of graph, including basically segments, squares, cubes, so like all regular lattice graph. So basically what Salez proved is that, well, at the beginning it was so that reservoirs made things more difficult. Perhaps they make things easier because, well, the question is not, well, cutoff is proved in many, many cases there, and it's still open even on the square lattice. Recently with Caputo, we have looked at like still one-dimensional systems, but in a continuum, okay, in order to make our method that is was very dependent on discrete tools more robust. Okay, people have looked also at things in irreversible setups when you have currents of particles, and in that case, the mixing behavior is very different, and also in a random environment. Okay, so I think this kind of concludes what I wanted to say. So what I would like to say last is a small word to an institute that we all cherish. So happy birthday, IMPA, and thank you for your attention.
Are there questions?
Thank you. So, not completely related, but very old question. So, you started with dynamical system of rigid balls, and then you moved to Markov chain, which changes the time reversal structure of the original equations to breaking it in Markov chain. So, can you comment? Do you have any rigorous way how to justify this transition or up to now? You know, this question is, I think it has 100 years old. But
yeah. So okay. So some people have been working on that. So there have been different aspects of this. Like you can start with okay. You have to take a relation between the radius of the particle and the density, so that collision happen on a certain scale. And then I think, yeah, under some assumption, you can prove that the particle in some scaling limit, if you fix one particle, then it converges to a random process. Okay, one individual particle, it will just look like a continuous time Markov process. And then if you rescale this process, it converges to Brownian motion.
it's not rigorous, right?
No, so some of these things are rigorous. I know that Bodino, Gallagher, and Saint-Raymond have worked a lot on this in the last 10 years, and they proved, they made really significant progresses. So there is still a lot to do, but they really did a lot. But yeah, I will not be able to give you any precise statement, but some stuff are known, yes.
More questions?
Hubert gave a very friendly talk, and wonderful to see it, but I promise you, if you look at the proofs, it's really, really hard work. With a team of students, we spent a month reading through these 50-page papers, and it's wonderful. So, it's not a question, it's a comment. But don't be fooled by... Take a look sometime.
More questions or comments? Well, I have a quick question. So can you say briefly what changes when you go from one dimension to two dimensions qualitatively?
So not much. So so in the asymmetric case, okay, let's talk about the symmetric case, because the asymmetric case is a bit different. But in the symmetric case, what's really different is, okay, in order to prove lower bound, actually, you can make things in 2 dimensions. There is no problem. The argument I gave you here, okay, you replace n to the minus 1/2 by n to the minus d over 2, and it works. But when you want to prove an upper bound, you have to make a coupling. So you have to really show that, okay, you can you can start a dynamic starting with from equilibrium, and one starting not from equilibrium, and couple them in that time. And the coupling device we have in these results really use the one-dimensionality. Basically, what you do is for each particle configuration, you're going to draw a line that goes down and up when you see particles and empty site. Okay, and when you see these two lines moving, okay, basically there is an order which is conserved by the dynamics. If something starts, okay, so the worst initial condition will be all particles packed to the right. The equilibrium will be something like this. And, well, you want these two things to meet at some point. And, yeah, so you have this correspondence in one dimension that helps you a lot because, well, this gives you, well, this thing is order preserving. And in two dimensions, you don't have anything like this. And therefore, you should, well, find a different path. And we don't have it yet. Okay, so I think some tools are needed.
No cutoff in
Yeah.
Okay, thank you. Are there more questions? So if not, yes, one more here.
By the start of the talking, you said that n is the number of slots in the system, and k is the number of particles, right?
Yes.
So every time you showed us this final.
K was n over 2, yes.
Oh, okay.
Yeah, but, yeah.
There is k inside of this final result, because I can see only n.
Oh, yes.
There is no k. There's no
Yes.
dependence of the number of particles.
Okay, so here, k is here. Okay, k is equal to alpha n.
Okay.
And so the dependence in k appears here. Here you have no dependence in k at first order. But yeah, actually the result is valid for, okay, the mixing time would be 1 over pi square n square log k for a general number of particles as soon as you make it smaller than n over 2. So it was just for convenience that I wrote it like that. But you see that yeah, if you have a density of particles, then it does not depend on the number of particles at first order.
More questions? So if not, let's thank Hubert again.